Welcome back. This lecture is going to serve as an overview of what a probability distribution is and what some of its main characteristics are. Simply put, a distribution shows the possible values a variable can take and how frequently they occur. Before we start, let us introduce some important notation we use for the remainder of the course. Assume that uppercase Y represents the actual outcome of an event, and lowercase y represents one of the possible outcomes. One way to denote the likelihood of reaching a particular outcome y is P of y equals y. We can also express it as P of y. For example, uppercase Y could represent the number of red marbles we draw out of a bag, and lowercase y would be a specific number, like 3 or 5. Then we express the probability of getting exactly 5 red marbles as P of y equals 5, or P of 5. Since P of y expresses the probability for each distinct outcome, we call this the probability function. Good job, folks. So, probability distributions, or simply probabilities, measure the likelihood of an outcome depending on how often it is featured in the sample space. Recall that we constructed the probability frequency distribution of an event in the introductory section of the course. We recorded the frequency for each unique value and divided it by the total number of elements in the sample space. Usually, that is the way we construct these probabilities when we have a finite number of possible outcomes. If we had an infinite number of possibilities, then recording the frequency for each one becomes impossible because there are infinitely many of them. For instance, imagine you are a data scientist and want to analyze the time it takes for your code to run. Any single compilation could take anywhere from a few milliseconds to several days. Often, the result will be between a few milliseconds and a few minutes. If we record time in seconds, we lose precision, which is something to be avoided. To do so, we need to use the smallest possible measurement of time. Since every milli, micro, or even nanosecond could be split in half for greater accuracy, no such thing exists. In less than an hour from now, we will talk in more detail about continuous distributions and how to deal with them. Now's the time to introduce some key definitions. Regardless of whether we have a finite or infinite number of possibilities, we define distributions using only two characteristics: mean and variance. Simply put, the mean of the distribution is its average value. Variance, on the other hand, is essentially how spread out the data is. We measure this spread by how far away from the mean all the values are. The more dispersed the data is, the higher its variance will be. We denote the mean of a distribution with the Greek letter mu and its variance with sigma squared. Okay, when analyzing distributions, it is important to understand what kind of data we are dealing with: population or sample data. Population data is the formal way of referring to all the data, while sample data is just a part of it. For example, if an employer surveys an entire department about how they travel to work, the data would represent the population of the department. However, this same data would also just be a sample of the employees in the whole company. Something to remember when using sample data is that we adopt different notations for the mean and variance. We denote sample mean as x bar and sample variance as s squared. One flaw of variance is that it is measured in squared units. For example, if you are measuring time in seconds, the variance would be measured in seconds squared. Usually there is no direct interpretation of that value. To make further sense of variance, we introduce a third characteristic of the distribution, called standard deviation. Standard deviation is simply the positive square root of variance. As you may suspect, we denote it as sigma when dealing with a population and as s when dealing with a sample. Unlike variance, standard deviation is measured in the same units as the mean. Thus, we can directly interpret it and is often preferable. One idea, which we will use a lot, is that any value between mu minus sigma and mu plus sigma falls within one standard deviation away from the mean. The more congested the middle of the distribution, the more data falls within that interval. Similarly, the less data that falls within the interval, the more dispersed the data is. Fantastic! It is important to know that a constant relationship exists between mean and variance for any distribution. By definition, the variance equals the expected value of the squared difference from the mean for any value. We denote this as sigma squared equals the expected value of y minus mu squared. After some simplification, this is equal to the expected value of y squared minus mu squared. As you will see in the coming lectures, if we are dealing with a specific distribution, we can find a much more precise formula. Okay, when we are getting acquainted with a certain data set we want to analyze or make predictions with, we are most interested in the mean, variance, and type of the distribution. In our next video, we will introduce several distributions and the characteristics they possess. Thanks for watching.